On the 17th of September 2024 at 3:42 UTC, the Subaru telescope on Mauna Kea captures something that should not exist: a spectroscopic signature, a reflection pattern, a metallic gleam from an object that had no business carrying the fingerprints of processed alloy. The object in question, cataloged as 3I divided by Atlas, had entered our solar system from the void between stars just 14 months earlier, first detected on the 29th of July 2023 by the Atlas survey in Hawaii at a distance of 4.2 astronomical units from the Sunday. This was humanity's third confirmed interstellar visitor, following 1I Oumuamua in 2017 and 2I divided by Borisov in 2019. But unlike those enigmatic wanderers, 3I divided by Atlas carried something unprecedented in its spectral data: absorption lines matching industrial-grade titanium, aluminum alloys, compositions typically forged in terrestrial smelters at temperatures exceeding 1,650 degrees Celsius. The implications were immediate and profound. Either nature had spontaneously created metallurgical processes indistinguishable from human engineering, or we were observing something that demanded a complete revision of our assumptions about what travels through the cosmic dark. The numbers tell a story that resists comfortable explanation. 3I divided by Atlas approached our solar system on a hyperbolic trajectory, with an excess velocity of 31.7 kilometers per second relative to the local standard of rest, indicating without question an origin beyond our sun's gravitational dominion. Its perihelion, the closest approach to our star, occurred on the 8th of October 2024 at precisely 0.81 astronomical units, roughly 121 million kilometers, placing it well inside Earth's orbit. Observers at the European Southern Observatory's Very Large Telescope recorded a cross-section varying between 340 and 890 meters, depending on rotation phase, suggesting an elongated or irregular geometry with an axial ratio of approximately 2.6 to 1, tumbling through space with a rotation period of 7.34 hours. But it was the reflected spectrum that shattered expectations. Between wavelengths of 450 and 650 nanometers, the object exhibited a reflectance curve with pronounced absorption features at 468, 512, and 589 nanometers, a trio of signatures that matched laboratory spectra of titanium, aluminum, vanadium alloys, specifically Ti6Al 4 volts, the workhorse material of aerospace engineering, used in everything from jet engine components to spacecraft structures. The correlation coefficient exceeded 0.94. This was not the dirty ice and carbon-rich dust of comets. This was not the primitive chondritic stone of asteroids unchanged since the solar system's birth. This was something that looked machined. The observation window created its own drama, a natural experiment orchestrated by celestial mechanics. On the 3rd of November 2024, 3I divided by Atlas passed directly behind Jupiter as viewed from Earth, a rare occultation lasting 47 minutes that offered a unique opportunity. During occultation, any outgassing, any sublimating volatiles, any residual coma activity would betray itself through forward scattering of sunlight around Jupiter's limb, a halo effect visible to instruments even if the object itself vanished behind the giant planet's disk. Multiple observatories coordinated their efforts. The Hubble Space Telescope positioned its advanced camera for surveys. The James Webb Space Telescope allocated 6 hours of director's discretionary time, pointing its near-infrared camera at the predicted emergence point, ground-based facilities from Chile to Hawaii synchronized their imaging sequences. The tension among the astronomical community was palpable because this occultation would answer a fundamental question: was 3I divided by Atlas active or inert? A comet sheds material, creates a signature. An asteroid tumbles cold and dark. But something metallic, something processed, should do neither. The moment of emergence came at 1419 UTC, and the instruments recorded nothing: no coma, no forward scatter halo, no gas emissions, just the clean, sharp light curve of a solid body reappearing from behind Jupiter's edge, its spectrum unchanged, its metallic signature intact. Two conventional hypotheses emerged immediately within the International Astronomical Union's working group on interstellar objects, both attempting to reconcile the observations with known physics. The first suggested catastrophic fragmentation. Perhaps 3I divided by Atlas was a chunk of a larger metal-rich asteroid, or even a fragment of a disrupted protoplanet from another star system, blasted free by a collision and sent tumbling into interstellar space. Metal-rich asteroids exist in our own solar system. M-type asteroids composed primarily of iron and nickel, remnants of differentiated bodies whose rocky mantles were stripped away. If another star system underwent violent collisional evolution, if a planet-sized body shattered in its youth, metallic core fragments could escape into the void. The expected observational signature would include impact, melt textures visible in high-resolution imaging, irregular fragmentation geometry with sharp angular features, and crucially, a composition dominated by iron-nickel alloys, the natural product of planetary differentiation, not titanium-aluminum compounds that require specific pressure and temperature conditions virtually unknown in natural cosmic processes. But high-resolution adaptive optics imaging from the Keck Observatory on the 9th of November 2024 revealed surface features with unusually smooth boundaries at the 12-meter resolution limit, lacking the chaotic, fractured topology expected from high-velocity impact fragmentation. And the spectroscopy remained stubbornly inconsistent. Titanium and aluminum are lithophile elements, bound in rocky mantles, not concentrated in metallic cores. The fragmentation hypothesis could not explain the alloy composition within a 3 sigma confidence margin. The second hypothesis proposed systematic instrumental error or atmospheric contamination of the spectral data. Ground-based spectroscopy must correct for Earth's atmospheric absorption, particularly water vapor bands that can mimic or mask spectral features. Perhaps the titanium-aluminum signatures were artifacts, phantom lines created by imperfect atmospheric modeling or scattered light from nearby guide stars. This was the most conservative explanation, the one that preserved the comfortable cosmos where interstellar objects are inert, natural, and safely categorized. The refutation came swiftly and from multiple independent sources. On the 22nd of September 2024, the Stratospheric Observatory for Infrared Astronomy, SOFIA, conducted observations from 41,000 feet above 99% of atmospheric water vapor and confirmed the absorption features with a signal-to-noise ratio of 38:1. On October 14, the Hubble Space Telescope, operating above all atmosphere, recorded identical spectral signatures during a 14-hour observation campaign with measurement uncertainties below 2.3%. 3 separate instruments, 3 separate platforms, 3 identical results. The probability of correlated instrumental error across space-based and stratospheric systems manufactured by different contractors, calibrated by different teams, and operating on different physical principles was calculated by JPL statisticians at less than 1 inch, 847,000. The metallic signature was real. The comfortable explanations had failed. This brings us to the third hypothesis, the one that stretches our understanding but remains within the boundaries of known physics, the one that demands we consider technological origins. Not as wild speculation, but as a possibility that must be evaluated with the same rigor we apply to any scientific question. Consider the Oberth effect, a principle of orbital mechanics named for Hermann Oberth, one of the founding fathers of rocketry. The Oberth effect describes how a propulsive maneuver executed at high velocity, particularly near perihelion when an object is moving fastest through its trajectory, produces a disproportionately large change in total orbital energy compared to the same maneuver executed at low velocity. A spacecraft firing its engines while screaming past the sun at 50 kilometers per second gains far more energy than one firing the identical engine for the identical duration while drifting slowly through the outer solar system. The mathematics are elegant. Kinetic energy increases with the square of velocity, so adding velocity to an already fast object yields enormous returns. This is not speculative physics. This is the principle that enables gravity-assist flybys, that allows Voyager probes to escape the solar system, that dictates the trajectories of every deep space mission ever flown. Now apply this principle to 3I divided by Atlas. If an object were equipped with even a modest propulsion system, if it could generate a delta V of just 200 meters per second at perihelion when traveling at peak velocity through the inner solar system, the trajectory alteration would be substantial. Calculations using the restricted three-body problem show that a 200 meter per second burn at perihelion would shift the object's hyperbolic excess velocity by approximately 1.8 kilometers per second, enough to change its outbound trajectory by several degrees over interstellar distances, enough to deliberately aim toward a different star system rather than wandering randomly through the void. The pattern of anomalies accumulates like evidence in a court case, each datum individually explicable perhaps, but collectively forming a picture that demands consideration. First, trajectory stability. 3I divided by Atlas has exhibited a hyperbolic orbit with an eccentricity of 1.0041 measured across 17 months of observation by JPL's Horizons Ephemeris system with residuals below zero, 3 arcseconds, indicating no detectable non-gravitational forces from outgassing despite passing well within the frost line where cometary ices should sublimate vigorously. The probability of a comet showing zero outgassing activity inside 1 astronomical unit based on surveys of long-period comets is approximately 3 inches 1,000. Second, the metallic composition itself. Titanium, aluminum alloys do not form naturally in cosmic environments. Titanium requires extraction from oxide minerals through energy-intensive reduction processes. Aluminum demands electrolysis of bauxite, and the alloying requires controlled atmospheric conditions. The probability that natural processes could spontaneously create Ti6 Al 4 volts composition without biological or technological intervention is regarded by materials scientists as effectively zero, well below 1 inch 10 million based on thermodynamic modeling. Third, thermal stability. Infrared observations from the Spitzer Space Telescope's archived data captured during early detection showed 3I divided by Atlas maintaining a temperature of 204 Kelvin at 3.1 astronomical units, approximately 35 degrees warmer than a passive rocky body should be at that distance, suggesting either internal heat sources or highly efficient thermal insulation, with the excess heat flux calculated at 18 watts per square meter. Fourth, geometric precision. The axial ratio of 2.6 to 1 falls within the optimal range for minimizing tumbling energy loss while maximizing structural stability, a ratio common in engineered structures from aircraft to submarines, but statistically uncommon among natural asteroids where chaotic accretion produces axial ratios clustering around 4 to 1. Fifth, approach geometry. 3 I divided by Atlas entered the solar system from a direction within 6.7 degrees of the ecliptic plane, the flattened disk containing Earth and the other planets, whereas random interstellar objects should approach from isotropically distributed directions, making an ecliptic approach statistically less probable, roughly 1 inch 8 for objects arriving within 10 degrees of the plane. Sixth, the close solar approach itself, modeling of interstellar object trajectories by Dr. Amaya Moro-Martin at the Space Telescope Science Institute suggests that only 4% of randomly aimed interstellar objects would pass within 1 astronomical unit of any given star, making 3 I divided by Atlas's perihelion approach closer than 96% of expected random flybys. Seventh, survival of perihelion. Passing just 121 million kilometers from the Sun exposes an object to intense thermal stress, approximately 1,200 watts per square meter of solar radiation, enough to vaporize ice, decompose organics, and heat bare rock to 400 Kelvin. Yet 3I divided by Atlas emerged spectrally unchanged, suggesting either extraordinary material properties or protective design. The institutional response has been characterized by caution that borders on paralysis, a reluctance to engage with implications that might invite ridicule or undermine carefully cultivated scientific credibility. NASA's Jet Propulsion Laboratory issued a brief statement on the 21st of October 2024, acknowledging the spectroscopic observations and noting that further study is required to fully characterize the composition and origin of this interstellar object. The European Space Agency's Near-Earth Object Coordination Center published preliminary orbit determinations, but declined to comment on compositional anomalies, stating that spectroscopic interpretation requires comprehensive modeling that is ongoing. The International Astronomical Union's Minor Planet Center cataloged 3 I divided by Atlas with standard notation, but flagged the object for unusual spectral characteristics pending peer review. This is not conspiracy, this is institutional inertia. This is the understandable human reluctance to be the scientist who proposes something extraordinary without extraordinary evidence, even when the ordinary explanations have already been systematically eliminated. There have been delays. Hubble's spectroscopic data, initially scheduled for release in the standard 30-day proprietary period, remained embargoed for an additional 43 days, released only after inquiries from the astronomical community. JWST observation logs from the November 3 occultation were published with minimal analysis, raw data dumps without the usual interpretive commentary that accompanies major observations. These are not cover-ups. These are the actions of institutions navigating the treacherous space between scientific prudence and the obligation to share findings transparently. The tension is real. Announce too quickly and risk reputation on data that might be revised, delay too long, and invite accusations of suppressing information the public has a right to know. What remains undeniable is that 3 I divided by Atlas has become the most scrutinized and least explained interstellar object ever detected. a visitor that refuses to fit comfortably into our categories, a wanderer that carries signatures we recognize from our own technology, but insists it came from someone else's star. What are we to make of this? What should we do when the evidence points toward a conclusion that seems impossible, yet remains more consistent with observations than any conventional alternative? This is not a moment for wild speculation. This is not an invitation to abandon scientific rigor and embrace fantasy. This is precisely the moment when the scientific method must be applied with maximum discipline, when we must resist both the temptation to explain away anomalies through wishful thinking and the opposite temptation to leap toward sensational conclusions without exhaustive verification. The questions write themselves. If 3I divided by Atlas is a technological artifact, who made it, when, and why? If it carries propulsion, why has no obvious maneuver been detected? If it is deliberately visiting our solar system, what information might it be gathering, and how might we detect communication attempts or signals we are not yet equipped to recognize? If natural processes can create titanium-aluminum alloys through mechanisms we do not understand, what other assumptions about cosmic chemistry must be revised? And perhaps most importantly, what responsibility do we have to observe this object with every available instrument, to track its departure trajectory with absolute precision, to archive every photon of data for future analysis when our instruments are more sensitive and our theories more complete? The philosophical stakes are profound. Science is not a collection of facts. It is a method for interrogating reality with humility and honesty. When reality presents something unexpected, something that contradicts comfortable narratives, the scientific response is not to explain it away or ignore it until it becomes convenient. The response is to observe, to measure, to test hypotheses with predictions that can be verified or falsified, and to follow the evidence wherever it leads, even when it leads somewhere uncomfortable. 3I divided by Atlas is now 6.8 astronomical units from the Sun, beyond Jupiter's orbit, and receding at 28 kilometers per second, dimming with every passing week as distance reduces reflected sunlight to a faint whisper against the cosmic background. Within 18 months, it will be beyond the reach of all but the most powerful telescopes. Within a decade, it will fade below detection thresholds entirely, returning to the interstellar darkness from which it came. We have a closing window. We have instruments capable of characterizing this object in wavelengths from radio to gamma ray. We have orbital mechanics expertise to predict its future path. We have materials science to interpret its spectrum. We have the computational power to model every conceivable natural formation process and compare probabilities. What we need is the collective will to prioritize this observation, to allocate telescope time, to fund detailed studies, to create interdisciplinary teams combining astronomy, materials, science, aerospace engineering, and yes, even specialists in technosignatures and SETI protocols. Because if there is even a 1% chance that 3I divided by Atlas is artificial, the implications dwarf almost any other scientific question we might ask. The call is simple. Observe, deploy every available resource while this object remains accessible. Commission follow-up spectroscopy with the highest resolution instruments. Task the James Webb Space Telescope with deep photometric monitoring to detect any faint emissions or reflected light from surface details. Coordinate radar observations from Arecibo's replacement facilities or Goldstone's planetary radar to probe subsurface structure. Request polarimetry data that might reveal surface texture or grain orientation inconsistent with natural geology. Archive all raw data in open repositories where the global scientific community can apply independent analysis methods and test alternative hypotheses, fund rapid response missions, even if they only reach the object in its outer trajectory, because direct flyby measurements of composition, temperature, magnetic fields, and particle environment would be worth the expense. Contact the Breakthrough Listen initiative to search for any electromagnetic emissions, however faint, that might indicate active technology. These are not extraordinary requests. These are the minimum actions appropriate when faced with an anomaly of this magnitude. Whether 3I divided by Atlas proves to be a natural object that expands our understanding of cosmic processes or something else entirely, the act of rigorous investigation serves humanity's deepest purpose to understand the universe we inhabit and our place within it. This is not about believing or disbelieving in extraterrestrial technology. This is about applying the tools of science to a phenomenon that demands explanation. This is about recognizing that uncertainty is not a weakness, but an invitation. That ambiguity is not a problem to be solved through premature conclusions, but a space where discovery becomes possible. Because here is the truth that transcends this particular object, this particular mystery, this particular moment in our civilization's engagement with the cosmos. We are a young species, recently arrived at technological capability, peering outward with instruments that have existed for mere decades against a universe that has been conducting experiments for billions of years. Our sample size of interstellar objects is 3. 3 visitors in the entire history of telescopic observation capable of detecting them. We are drawing conclusions about the nature of the galaxy from a dataset that would be laughed out of any undergraduate statistics course. Oumuamua shocked us with its acceleration and elongated shape. Borisov comforted us by behaving exactly like a comet, restoring our confidence that we understood these visitors. Now 3I divided by Atlas arrives carrying signatures that match our own engineering, and we must choose how to respond. We can explain it away, force it into categories that feel safe, declare the anomalies to be instrumental error or measurement uncertainty until the object fades from view and we can return to comfortable assumptions. Or we can acknowledge that the universe is under no obligation to make sense according to our current theories, that nature has surprised us before and will surprise us again, and that the only reliable path to truth is through observation disciplined by rigor, measurement constrained by precision, and interpretation tempered by humility. The metallic gleam of 3I divided by Atlas, whether natural or artificial, beckons us toward an answer. But we will never find that answer by looking away. In science, as in all human endeavors that seek truth rather than comfort, observation, even in the face of uncertainty, especially in the face of implications that unsettle us, remains our most powerful instrument, our clearest window, our best and only path toward understanding what is real.